Okay, so we are on page 9 of the Unit 2 notes, and today's topic is error. Excuse me. So error is the difference between an experimental or measured value and an accepted value. This could take a couple of different forms. So the accepted value could be something that you found in a table in a textbook. That would be considered an accepted value. It could be another calculation. For instance, in a later unit, we know that when we have a certain amount of chemical that's going to react, we can calculate how much product we should have at the end. That calculation is what we would consider the accepted value, and the experimental value is what we actually measure. So, in terms of a chemical reaction, if we're talking about mass, our experimental value might come from the balance. This is where we actually measure the mass. And the accepted value would come from calculation. So error, being the experimental value minus the accepted value, could also be thought of as the number that comes off of the balance minus the number that we got in the calculation. So let's look at some mass numbers, and these are made up numbers. But let's say my calculated mass is 25.0 grams, and let's say my balance measurement is 24.5 grams. So these are the numbers that we're working with. So the error here is the experimental minus the accepted, or the number that I got from the balance, 24.5 grams, minus the number from the calculation, 25.0 grams. And so what we find is an error is negative 0.5 grams. What this is really saying is that we have 0.5 grams less than we expected. Let's box that off. So negative 0.5 grams is 0.5 grams less than expected. So now let's say that we messed up our significant figures, something that we've been talking about for a few sections now. So we look at our balance and we measure it at 24.5 grams, just like before. But let's say in our calculation, let's say we changed the significant figures and we came up with 25 grams. Now, the rules for addition and subtraction with significant figures are fairly specific. And it says that the number with the least digits following the decimal is the one that determines the significant figures. So we have a decimal with one digit, and here we have an implied decimal with nothing after it. So when you subtract these, it is 0.05 grams, but with significant figures, it's negative 1 gram. This is with the significant figures that were determined by this number. And so some premature rounding right here caused our error to double just because of rounding issues. So we need to be careful with significant figures. And I'll write this as a note. The significant figure difference doubled the error. Now, did anything actually change? Probably not. It was probably exactly 25 grams, just like above. The only issue is that we forgot the 0.0, and that changed the digits that were required. So just an illustration of something that could happen if you don't follow your appropriate significant figures. See, this number is more accurate than this number, so we have to be careful with those. Error can be misleading if you present it incorrectly. To get a better idea of the big picture, we use something called percent error. This expresses the error as a percentage of the accepted value. So percent error is the absolute value of the error divided by the accepted value times 100 makes it a percentage. So let's use the numbers that we had above. So our error, and I'm talking about this one with the appropriate amount of accuracy, absolute value of negative 0.5 grams divided by the accepted value, which was our calculation of 25.0 grams. Times 100 makes it a percent, and we find out that the percent error is 2%. This 2% is based on significant figures. So this top number, negative 0.5, has one significant figure. The bottom number, 25.0, has three significant figures. And so our answer should have one significant figure, and it does. It's 2%. Here's a statement. I was only off by 5 feet. Is this statement implying that I was close? Or was it implying that I was way off the mark? Hard to tell. It's going to depend on the accepted value. 5 feet is the error. No question there. But it doesn't give us the whole story. If my target is 500 feet away, 5 feet off the mark is pretty good. The percent error here is 1%. So we're looking at absolute value of 5 feet divided by 500 feet times 100 makes it a percentage. So my error there was 1%. In science, an error under 5% is considered excellent. It's like the gold standard. In statistics, under 5% is the goal. If you're doing an experiment and your error is greater than 5%, then there's some sort of issue that needs to be addressed. And this can help us identify problems within the laboratory by looking at our percent error. I was only out by 5 feet. So if my target is 20 feet away, 5 feet off the mark is really bad. The percent error here, 5 feet over 20 feet times 100 as a percentage, 25%. 25% error. That would be really bad. Using the percent error gives us a reference. So a 1% error is good. A 25% error is bad. Only off by 5 feet, it's hard to know either way.